All right, so today we're going to talk about something called the Dariac delta function. This is a very unique and critical function when it comes to physics applications in other science courses, which we're kind of jump into an application part here. So before we get into the transformed mode of this, and so I kind of want to show you, you can see in the definition of the delta function, they have that transformed piece. So before we get into that, I thought it'd be interesting just take a couple minutes and go back into a basic Dariac delta function and just talk about what does the basic function do, and then hopefully that'll help make this transformed function make a little bit more sense for us. Okay, so what is the Dariac delta function? On the surface, the basic one looks like a step function. And I say like a step function, I say a little bit of hesitation. You'll kind of see in a second what I'm talking about here. But the function itself is defined where at the number 0, it has an infinite height, and everywhere else it's 0. So if you think about it in terms of, say, like a physics setting, it's you're watching something happen and nothing happens for the most part, and then all of a sudden instantaneously you get a pulse and then you go back to nothing, right? And so we're focusing the conversation about that pulse. What happens that moment where you get energy in the system? What happens that instant that happens? So on the surface that doesn't sound that exciting or interesting, but hopefully by the end of the lesson we'll see some places that we can utilize this idea. Okay, so because the way we define this, that our piecewise function essentially is 0 for the most part, and then at one instant it's an infinitely tall function, we then tack on the definition that the area of the entire curve, the area of that one function, is equal to 1. So it's a unit rate function, which allows us to bring in some other concepts we've seen. So if we zoom in about what happens close to 0, if we zoom in at that piece right there, we're saying before we hit close to 0, and right after that same similar distance, we have nothing. The y value is 0, and then at a certain point it jumps up to that height. And so because we're saying the unit area is equal to 1, we kind of think of it like a delta epsilon proof from way back in Cal 1 days. And so at a certain epsilon away from 0, we all of a sudden hit a sudden step, right? And that's why we kind of relate it similar to the unit step function. But at epsilon away from 0, we all of a sudden jump up to an energized state where we have a y value. And to help us see why we define that unit area to be equal to 1, we just define that the height is 1 over 2 epsilon. So 2 epsilon meaning the width of our rectangle is 2 epsilon wide. So our height is mirrored so that the area under that curve is defined to be 1. And then we can then apply our unit step definitions. So we can rewrite our delta function as unit step from negative epsilon to epsilon, and that allows us to take the limit as epsilon approaches 0, so that we get that epsilon to get infinitely smaller. The closer and closer to 0 it gets, then that height gets larger and larger. Now, why does that matter? Why do we care? What's so special about that? Well, what matters is when we try to take that moment of energy and compare it to a function value of some type. So if I'm integrating, say, from negative infinity to infinity of f of x times this delta, and I just realized I have 2 dx's. I don't need 2 dx's. But if I'm integrating of f of x times that delta, right, that delta function, the area of it, is equal to 1. And so if I treat as that moment when x approaches c, right, that's that one place that it has that function value, then this part over here, that's by design all equal to 1. It's all equal to 1. And so I'm left with the height at that particular transition point. Okay, so it's a little bit thick in theory here, but it essentially the delta function allows us to track and investigate moment impulses in an energy system. Okay, so I hope that brief distraction kind of will help this more complicated system make more sense. So we first define something called a unit impulse, and so I'll just kind of go with the textbook definition. So mechanical systems are often acted on by an external force of large magnitude that acts only for a short period of time. For example, a vibrating airplane wing could be struck by lightning. A mass on a spring could be given a sharp blow by a hammer. A baseball could be sent soaring when struck violently by some club. And if we look specifically at, say, the golf scenario, and we track what happens to the ball, right before the club hits the ball feels nothing, and then there's that one moment where it gets an impact, so there's an instantaneous increase of force, and then after the club has hit the ball, it doesn't feel anything, right? So what happens at that one particular moment? And so this then brings up the transformed form of this, where we have our delta function at t minus t naught. So the difference between the time it hits the ball versus the start of the time. So when that distance gets smaller and smaller and closer to zero, kind of had that brief exploration there. But you can see this nice complicated function we can break up into before it hits the ball, while it hits the ball, and as it hits the ball. So let me highlight this. Is before it hits the ball, it has the force has a magnitude of 0. While it hits it, it has that magnitude, and then after it leaves it, it goes back to having a force of 0, and it's just acting on that energy. And so you can see in the graph, kind of what I've shown with the simple form, is if we're A units before and A units after, then the height of that rectangle has to be 2A. So this is the graph right here, is an attempt to show as you get closer and closer what happens to the height. Right, so here we're a certain distance away, so the height's pretty small, but as you get closer to that impact point, the height of your force is going to increase until, what does that part mean? That means you've got an infinitely tall y value that measures the impulse. And so we define that to be a unit impulse. Okay, so the unit impulse we find is easier to measure with that Dariac delta function, and specifically transformations of it. But like anything we've seen in this unit, we look at these complicated things so that we can use previous techniques in the effort to make our lives easier when dealing with complex functions that we just did not know even existed. Okay, so all of this fancy talk to simply define this one new transformation, and that's the transform of the Dariac delta function. So we have this new symbol, and that's the key component. That's the part that's going to show up on a formula chart for how do we do a Laplace transform of a Dariac delta function, and there we go. Laplace of Dariac delta of t minus t naught is e to the negative s t naught. So we just have to identify what t naught is in the problem and pretty much go from there.